I'm kind of getting. I want to know more about phases and about manipulating phases and all that stuff. I think so. An eye opener for me was reading the Programming Quantum Computers book from O'Reilly, where they showed a couple of examples of things you could use phases for, to sort of encode results of some arithmetic operations and stuff like that. And then I don't know. I hadn't, until reading that book, I really hadn't seen that these ways. So for me, I had a bit of a different understanding of the whole thing, and by then I liked to think more just about the amplitudes and then the complex side of uncertainty and all this kind of stuff. But I was kind of ignoring the phases a little bit. But now I'm getting a bit more into this, and I see also phase kickback and stuff like that. So I want to read more about this. I want to explore more. So this is one of those. So this is one video where I found this in the algorithmic assertions blog. I just want to think. The title seems like it fits the mood that I have right now. So I kind of feel like diving into this a little bit more, see what happens. So in this post, I'm going to explain a trick for phasing quantum states in a convenient and flexible way. Sounds useful. Basically, the trick involves preparing ancilla qubits to act as proxies for the states you want to target. Then phasing those ancilla, that's the name proxy phasing. So we'll start simple, but by the end of the post, we'll be phasing each state by an arbitrary computable function of that state. Proxy phasing 1 qubit. As promised, let's start with something simple, even trivial. Instead of phasing a qubit directly, so that's the phase gate, we exactly. So here's the phase gate. So we can temporarily C-naught it into a clean ancilla and phase the ancilla. Okay, yeah. And phase the ancilla. Yeah. If you pay attention to the beat values that define the computational basis states and understand that a Z gate on a qubit phases any state. Yeah, exactly. That's true. That's understand that a Z gate on a qubit phases any state where the corresponding bit is 1. It's clear why phasing the ancilla is phasing the original qubit. Here's what happens. I mean, because you're doing a control knot. So if this qubit is 1, then you're going to negate the ancilla, you're going to apply the phase gate. So you're basically phasing the state 0, 1 in this case, because you're then going to apply a control knot again to reverse that. The system starts in the state this. We introduce the ancilla. Yeah, so that's kind of meaning it's an unknown state. So that being this qubit here, this wire here. We introduce the ancilla producing the state or I keep messing up with the notation. So okay, so this is the other way around. So this is the upper value and the lowest value. Exactly. So this is because you see here. So the 0 is the second. But again, we read that. So if this is the ket, like this would be equal to number 1 in binary, right? So that's, and then this is this qubit. Okay. So that's not correct. So this is exactly, so 0, 1, 1, 0 in this case. Okay, so 0, 0, 1, 0, yeah. We apply the first control knot transitioning to the state 0, 0, 1, 1. Notice that the first qubit always agrees with the second bit. We apply the Z gate. This applies a phase factor to states where the qubit is 1. If we apply the Z gate to the first qubit, it phases the 1, 1 component because the first bit of the component is 1. If we apply the Z gate to the second qubit, it phases the 1, 1 component because the second component is 1, 1. Neither of the two locations would phase the 0, 0 component because that component's bits aren't 1. The location of the Z gate does affect whether the 0, 1 and the 1, 0 components would be phased, but those components aren't present in the state we are operating on. The two possible operations have the same effect on the components that are present, therefore they are equivalent. Whether we target the original qubit or the ancilla qubit, we find ourselves in the state 0, 0 minus, so the phase here 1, 1. We uncompute the ancilla by applying the second C0. It leaves us in the state A0 minus 1, 1, which is what we wanted. Okay, interesting. Yeah, I mean, here I assume that was 1, right? Okay. But this is then, okay, so this is kind of uncomputing. Yeah, okay, so it means we ignore the beat here. No, but it's interesting. It's interesting how, yeah, okay, that's kind of the basic case. So you're basically phasing a qubit by phasing an ancilla that you're doing a control knot with, but this will be the equivalent of doing that. So it's just to illustrate, I guess, what is coming next. In general, if two qubits are guaranteed to agree, then you can move a Z gate from one to another without changing the function of a circuit. Guaranteed to agree is a bit vague. What it means is that if you were to do a computational basis measurement of the two qubits at the relevant time, there is no chance the measurement results would disagree. See, knotting a qubit onto a clean ancilla is the simplest way to create such a state. Note that we can uncompute the ancilla qubit with entanglement erasure instead of with the second C0. Okay, entanglement erasure, I haven't checked that, although I have apparently clicked on the link before. And you won't see that right now. I'm just checking this. Okay, that's something that I have pending to take a look at. Okay. But I'm assuming it's about disentangling, right? Because it basically says, I'll probably do that in a separate video, but a Bell pair set qubits, you might expect the qubits more entangled because manipulation reduced to Bell pair. Yeah, so it's about disentangling. I think this is really about disentangling. Okay. There's like there's a puzzle. Okay, nice. Yeah, I'll take a look at this later. See if we can move without it. But basically, now that we can uncompute the ancilla qubit with entanglement erasure instead of with the C0, so you do that. Then, yeah, but what's the point? You phase the ancilla, then you apply a Hadamard and measure. So, and based on the measurement, we apply a Z gate or not. Because the idea is, if you, after applying a Hadamard, if you would actually measure a 1, it means that you were in the minus state, and so then you want to apply a Z gate there. Yeah. Kind of. Okay. What's the point? The above equivalence is a key part of magic state distillation. Okay, I haven't done this either, so maybe this will be more relevant by then as well. Universal connection with ideal clarification and ancillas. Okay. The above equivalence is a key part. For example, the surface code is a quantum error correcting code that's not normally able to apply T gates. But you can 45 degrees rotations around the Z-axis. But you can see not a surface coded qubit into a clean surface coded ancilla qubit, unwrap the ancilla into a raw physical qubit where 45 degrees options are possible, and do the phasing there. Oh, I have just started exploring surface code. So if this would not be available, basically you see not, I don't know what it would be unwrapping in this case. Okay, I get it, but I get what I mean. I don't get it, but what I think this, my intuition is telling me this has to do with, a practical a practical situation where this would come in handy is exactly um, when you have those surface codes that are not able to do this 45 degrees. So you would actually do the rotation in somewhere where it's kind of where you can actually do it, and then based on those measurements you would do something with a logical qubit. I don't know. Uh, but here's the Z, so that's like another 45. Okay. Mm. Oh, the Z is to correct the cases in which you don't want that phasing, I guess. I guess what this does is I mean, that is if you measure a 1, right? That's what it means. Let's see. Proxy phasing combinations of qubits. Uh, Interesting. Suppose that we see not multiple qubits into a single plane ancilla. Then phase the ancilla, what happens? Hmm. I mean, my first guess without reading any of the stuff below is that this phase would actually accumulate. So let's say your angle is, oh man, I'm so bad. Let's say angle is like 10 degrees, right? So what would happen here in this case is that you would end up with a state where the 111 component would be, the 111 term would be phased by 30 degrees, whereas the like component terms with two ones will be phased by 20 degrees, and terms with one would phase by 10 degrees. That's what my intuition tells me, because basically I have the impression that's what really, I don't know, it's just intuitively I think that's what will happen. I don't know why exactly, but um to answer this question we ask another. If this was a classical circuit, what states would lead to the ancilla bit being on? Oh crap, I actually forgot the fact that, yeah, it's not, no, it's not like that. It's the, okay, so this is only about, like for example, 111 will work, 110 would not work, because, so it's only, okay, so it's only for those cases where you have an uneven number of ones. So it's either the terms that have one or that have three ones in this case. So that would not be true. Hmm. Well, each xenon may or may not toggle the ancilla. If there's an odd number of toggles, exactly, the ancilla will be on. If there's an even number of toggles, the ancilla will be off. And our circuit toggles the ancilla bit once per each input bit that's on. Therefore, the ancilla bit will be on if the input state has an odd number of set bits. Yeah. Now back to the quantum case. All the operations that are present permute. Now back to the quantum case. All of the operations that are present permute the computational basis without mixing, interfering any of its elements. There are no Hadamard operations. Okay, so all of the operations that are present permute the computational basis. Don't know, not entirely sure what this means. without mixing or interfering any of its elements. A permute, okay, this means they just, yeah, okay, so you're just flipping ones and zeros. And there's no interference. There's no here like, terms disappearing or canceling out and whatnot, because there's no Hadamard operations. Because of this fact, we can basically directly apply what we learned when considering the classical case of the conditional basis states with an odd number of set bits. The ancilla qubit ends up on for other states. For other states, it ends up off. For example, the input state, this will expand in to the intermediate state like this. Exactly. Speaking a bit more abstractly, the three C-naughts transition the system from state into the state blah, where P is a parity function of the rest of the case. Hamming's way is odd or even is reasonable to describe the situation as the ancilla qubit is storing the party. So when we face the ancilla, we're facing that party. States where the party is 1 get phased, and states where the party is 0 don't get phased. Okay, but the phase doesn't accumulate, so I was wrong. Just let me just try that. Let me just try that. So can I just do this? So this, then we'll do let's say a quarter turn, and compute, and then this, oh sorry, this is going to be another one here. Well, just how it was done exactly like this. One more here, here, and here. And I want to measure this 3 qubits. And what happens if we are with, for example, 1, right? So this is exactly its phase 90 degrees, which is what the S does. But if it's 1, 1, 1, okay, so that doesn't accumulate. Oh, wait a second. It's a phase. Okay, because that's the relative one. That's what we're looking at. 1, 1, 1. Okay. So it's just at the parity level. So if it's 1, 1, 1, then that's the state. That's the term. If we are in a say superposition, right? Which elements are phased? This element is phased 90 degrees, this is phased 90 degrees, this is phased 90 degrees, this is phased 90 degrees. Exactly. Makes sense. Okay. Good. So where was I? Okay. Now back to the quantum case. We saw this. Speaking a bit more abstractly, the 3 C-naught transitions system. Yeah, this okay. We check by this angle. Okay, yeah. This concept generalizes to phase the set of states matching a predicate P. You compute P prime, and store the result into an ancilla A. Then phase A by the desired amount, then uncompute P prime. Any set whose membership can be computed and can be phased in this way. The easier it is to compute a set, the easier it is to phase that set. Predicate P phase P prime. Okay. So we're using Grover's algorithm to search for variable assignments that satisfy three-step problem. This requires you to apply a phase factor of -1 to all of the satisfying variables assignments. But how can you phase the very thing you're looking for without already knowing where it is? That's where proxy phasing comes in. Apply a reversible circuit that outputs whether the inputs are a satisfying assignment to the problem, and then apply a Z gate to the output qubit and compute the circuit, and you've done it. To the output qubit. Okay, a reversal circuit that outputs, okay, the output being one qubit that flags the solution. So being, if I understand this well, is let's say you've got um, okay, so let's say you've got like 3 or 4 wires, right? And then this here's your output one. So and you basically have like your circuit in here that encodes that basically creates a superposition where that qubit in here is going to be 1 if that particular term is a solution or not as a solution, and a 0 if it's not a solution. And so because of that, the only thing you need to do here is apply a Z gate, because then that's you're exactly flagging those states where the 1 is there. That's kind of what's being mentioned at the very beginning here, right? Here. Exactly. Yeah. Phase gradients. Being able to construct a nice circuit for phasing a set of states is great, but often you'll want more fine-grained control than just phase or not phase. In particular, suppose that we want to, yeah, that's okay. I think I know what this is going. This is going towards encoding stuff in the phases in a way that is more granular, like specific rotations. And I think that's really what's happening in phase estimation, actually. But often you'll want more fine-grained control than just phase or not phase. In particular, suppose we want to phase each computational basis state k by k c radians for some constant c, such as c equals this. I call this kind of operation a phase gradient or linear phase gradient. Yeah, okay. So this basically means that this is sort of your unit, like your precision in that sense, and to some extent that's in some sense that's your precision. And then if your k equals 4, right, you want to phase it in a way that's proportional to that 4, but that jumps this, right? So this is actually quite simple. Let me clean up this. Because of the binary to unary relationship between the qubits and the state indices. Assuming the qubits are in little endian order from top to bottom, we simply phase the top qubit by this, the next qubit by this, exactly the next by this, and so forth until the bottom end qubit is phased by that. Yeah. So you're phasing, each qubit has its own weight, right? Because it's still binary. When we measure, it's still a binary representation. So basically, that the lower you go, the higher the weight this qubit has in the number, right? And the overall representation, if you're representing a decimal number, but with binary, in binary. To understand why this works, consider state 01011 is 11 in binary, so we want to phase the state by 11 times pi divided by 1000. When we phase the qubit, state is phased if and only if. Okay, but I think that's because I had seen that before in phase estimation. That is why this whole thing led me to, for some reason, believe that these things would accumulate. But I'm again as ignoring about the fact that this is a superposition and there were. I think I'm getting confused. Let me just go ahead. So only has one qubit. It says even only if it has a 1 at that qubit's position. In this case, the state will be affected by phasing applied to the first, second, and fourth qubit, but not by phasing applied to other qubits. If we combine the phasings, yeah, okay, but that's what I mean, right? So they add up, and that's what kind of led me to think that these things would add up. And but I just basically got confused. Did I get confused? Hmm. Which is what we want in 11. The reason this was is because we're matching the phasing of each qubit to its weight in our binary encoding of numbers. That's what I said exactly. The fourth qubit is a weight of 8. Yeah. The weights of the set bits add up to number we want to represent, and the phasing effects add up in exactly the same way. Now that we have phase gradients, we can start using them on proxy qubits, but then maybe I'm missing some nuance in here. Why doesn't this phase 111 by 3 times theta? Oh, because it's just one operation being performed. Yeah, okay. You're just phasing one operation. Like it's just phase. Yeah. Yeah. It's almost like literally this, right? I mean, not in this case, because the idea of breaking this down with control node is that then you're actually getting that as an outcome. But my point is it's one operation that's being applied, and here it's multiple phase operations. I think this is where my intuition went wrong. Okay, cool. So fairly simple until now. Computed phasing. Suppose we want to phase each state k by some function f of k that isn't of the form c times k. For example, suppose we want to phase each computational basis by k to the power of 2 times pi divided by 50 radians. We can construct a reasonable circuit to do that. Or can we construct? Yeah. Yes, we can. And as you might guess, based on the content so far, the trick involves a circuit that computes the function we're interested in phasing by. Exactly. And then that result is the one you're encoding. And this is what phase estimation is doing, is it's calculating these modulo power functions, or however you call that, and then encoding the result in the phase of a particular qubit. And yeah. Go check the phase estimation video. Suppose we want to phase each state. Can we make a trick involves a circuit that computes the function we're interested in phasing by. We want to phase by an amount proportional to k times k. So the first thing to do is construct a classical reversible circuit to compute the square of an input. Second, we use this circuit to store the input square into an ancilla register. Third, apply a phase gradient to the ancilla register. Lastly, uncompute the ancilla register to phase by a different function to replace squaring with any other computable function f. So this is the function, and this would be the squaring. Then you're phasing proportional to that, and then you're uncomputing. Keep in mind that the phase gradient can absorb pesky constant factors. The phase gradient can absorb pesky constant factors. Also keep in mind that for most choices of f, you will want to compute an approximation rather than an exact result. The result must be stored in fixed point arithmetic, not floating point arithmetic, for the phase gradient construction to make sense. Applications. The fact that you can phase by any computable function is useful to keep in mind. For example, consider a circuit that nodes n qubits by that rotates n qubits by theta radians. This effect is so simple that you might assume it is impossible to optimize beyond just applying z rotations, the z rotation gate to each qubit. But knowing about computed phasing, you may feel prompted to ask, what's the function that the circuit is applying to the state? Is there a fast way to compute that function? Consider the state 011001. How much is this state phased by applying an RZ to every qubit? The RZ operation doesn't phase zeros, but phases ones. You see here, this is again confusing me, because if you take a look at Quirk, it does phase zeros if I just apply a rotation. How much is the state phased by applying RZ theta to every qubit? The RZ operation doesn't phase zeros, but phases ones by theta. The state has 3 ones, so it will be phased by theta 3 times, totaling 3 times theta. Other states follow the same rule. The number of Z bits determines how much phasing happens. State K will be phased theta times, where it's the Hamming weight function. Okay, so instead of rotating the n qubits individually, we can make a circuit that computes the Hamming weight of the qubits, adds them all together, apply a phase gradient to the LGN qubits, making up the Hamming weight register and uncomputed. Surprisingly, when performing error-corrected computation, this can be cheaper than applying the individual rotations. Okay. Arbitrary rotations by some theta have to be synthesized by combining a fixed state of available rotations with the dominant cost being the number of T gates. Okay, as your desired accuracy gets smaller, more and more T gates are required. It can take dozens of T gates to synthesize a good enough rotation. By contrast, temporary counting up n qubits takes roughly 4 T gates per qubit. Interesting. Suppose it takes m T gates to synthesize one accurate enough rotation. The cost of individually rotating all n qubits would be m times n. But the qubits would be blah blah blah. Even if m is 20 and n is 3, this raises the count t from 6 to 44. As m and n get larger, the savings start becoming very big very fast. Synthesizing many rotations by theta hard is arbitrarily more expensive than synthesizing the same number of T gates. The phase by count construction guarantees that performing many rotations by any single theta always limits to at most 4 times as expensive as a T gate. That's an interesting observation. So it's easier to count and then make a rotation based on that parity rather than doing multiple things, because it becomes more expensive. Any computable phasing function can be applied with the cost of merely computing that function. Same is not true for magnitudes. Why? Any computable phasing function can be. Any computable phasing function can be applied with the cost of merely computing and computing that function. The same is not true for magnitudes. I don't understand the question, but I'll try to think about it. If you want to phase a specific set of states, make a circuit that temporarily computes membership in that set and applies a Z-gate to that computation's output. If you want to phase each state by an amount determined by a function, make a circuit that temporarily computes a fixed point register proportional to the function's output and applies a phase gradient to the output register. If you want to phase each state by an amount determined by a function, make a circuit that temporarily computes a fixed point register proportional to the function's output. When phasing qubits, consider how the underlying states are being phased. Is there an easy to compute function that picks out the affected states, or that determines how much each state is phased by? If so, computed phasing may be more efficient than a naive construction. Cool. Yeah, I mean, this is mostly kind of what I had intuitively learned from observing and breaking down the phase estimation algorithm. But it's nicely put. I think it's, yeah. Yeah, yeah, yeah. It's kind of a way to just, move information from the amplitudes to the phases. And I guess that has just a really wide range of applications in different algorithms. Cool.